Okay, our topic is extent of chemical reactions. So we've looked at rate, and now we're looking at extent. So rate, so if we do a bit of a recap, rate is essentially the change in concentration over the change in time, right? Whether that relates to the reactants or products, depending on how we look at it. So what does the word extent mean? In your own words. Anyone? TV, what does the word extent mean? Rate equals change in concentration over change in time. Delta C over delta T. The max of? Yeah? We're sort of getting somewhere. Where is it? Right, how far something can go, right? Or how much of. How much of, how far something can go. And, well, what's a chemical reaction? Well, what's our evidence of a chemical reaction? Right, so let's think about that. We've got different pieces of evidence for a chemical reaction. We've got permanent colour change. We've got the formation of a precipitate. I know my writing's terrible. Let's zoom in a bit more. Permanent colour change. We've got a gas or an odour released, right? And right, we might have heat given off or absorbed. Okay, so that's essentially what that means. And so that's the broader part of the topic. And then we get into this thing called equilibrium. But really we're talking about dynamic equilibrium. What does the word dynamic mean? Changing, or changing in what way though? So thermodynamics refers to what? I think of the word dynamic as being like movement. Yeah? So for something to move. So thermodynamics is the movement or the transfer of heat. Yeah? Let's break apart this word because you may not have heard of it before, unless you've watched the terrible, terrible film called Equilibrium. Anyone seen that film? Christian Bale, post-apocalyptic world where there's no emotions because you suppress them with a drug. No? Yeah, terrible film. I quite like Christian Bale as an actor. Yeah, no. His prime position was the 2001 film, The Newsies. So let's break down, what does this word mean? It's got equal in it. What does that mean? Yeah, so one thing is like equal to another. Equilibrium, equivalence, all of this, right? So we can sort of think about this as equal. I guess equal sides or something like that is, I guess, how we could interpret that. Yeah? Cool. So we've talked about a bit about open and closed system and the transfer of energy, right? And let's consider most reactions that we've explored so far are irreversible reactions. So what does the word irreversible mean? All right, can't go backwards. So irreversible, only one direction. So a combustion reaction is pretty much an irreversible reaction. So we've got reactants move towards products. That's it. Yeah? Can't go back the other way. So a reversible reaction right? Reverse means that it can, so in both directions. So we have reactants go towards products, but we also have products going back towards reactants. So a system that is at equilibrium, so a chemical system, yeah, is when the rate of the forward reaction is equal to the rate of the backwards reaction. So the net change in products, or the net change in reactants, becomes zero. So if I'm to look at this from a graphical point of view, let's look at the what's called the Haber-Fritz process. The Haber process. So there's this guy, 1918, named Franz Haber, German, of course, came up with this revolutionary chemical process. You may have seen it before. Anyone heard of Haber before? Anyone? No? The reason that this is revolutionary is because this, up until the early 20th century, there was what's called guano. Does anyone know what that is? Yeah? It's poo, yeah? Guano is like bird poo. It's incredibly rich in nitrates and phosphates, right? And they used to mine this highly valuable fertilizer, yeah? The Haber process allows us to get ammonia that then we can bubble through water and essentially get ammonium, which is a soluble form. So ammonia is a soluble form of nitrogen that has now revolutionized the agricultural industry, because we can mass produce fairly cheaply by taking nitrogen from the atmosphere, combining it with hydrogen that we can get through electrolysis of water, and get a soluble form of nitrogen that we can then use to fertilize plants. So 1918, this was formed. And so it's a German. So Germans had access to really great fertilizer, which meant they could feed their armies, etc. Except in 1919, Haber joined the German chemical warfare and came up with mustard gas. So he won the Nobel Prize for this in 1918. And as far as I know, the only person in history to actually have the Nobel Prize stripped from them a year later because of his involvement in the German chemical warfare and the formation of mustard gas. Right? Because it went against the idea of the Nobel Prizes in the first place. So Alfred Nobel, the guy who's named after the invention of dynamite, started by naming the Nobel Peace Prize because he realized the devastating effect that dynamite would have. And so going against those principles. Anyway, so let's just consider so if I look at time and my concentration of my gaseous species, and if I was to start with let's just say 1 mole of nitrogen and 3 moles of hydrogen. And if I started with nothing of ammonia. Over time, what we would notice is that the amounts of hydrogen and nitrogen would decrease and the amount of ammonia would increase. So we end up with something like this. So this is going to increase to a certain point. Nitrogen will decrease and hydrogen will decrease. So at this point here, so let's just call this T0, which is the point at which they're allowed to react. And sometime later, we notice that the amounts of them plateau out. So at this point, it says that the reaction has reached equilibrium. So if I was to look at the rate, instead of just the concentration, but look at rate over time, I would find the rate of production. So we'll have the rate of production of ammonia will go something like this. So this is the formation of NH3. And we find that the loss of the others decrease something like this. So this is the let's say rate of the reduction in reactants. So eventually the rate of the forward eventually equates to the rate of the backwards reaction. Does that make sense so far? Yeah, I could have had like the rate of reduction of H2 and N2, but I want to simplify that as just reactants in general.
What is your rank?
The reduction in reactants. So I'm just simplifying it as, the rate of loss of hydrogen and the rate of loss of nitrogen, just combining them together. If I wanted to, I could, do 2 separate lines. But we'll find eventually that the lines will plateau out anyway. The difference in here will matter, but not matter right now. So I'll get to that at another point in time. How do we find that? That makes sense? So far, so good? Cool. Talked about dynamic. Okay. So if I'm to look at this, go back to this idea of extent of a reaction. Extent. The extent of a reaction is measured by a proportion of the products over the reactants. So far, rate we haven't spoken about in terms of a quantitative process, whereas extent of a reaction we can. And we can do this by what's called the equilibrium law. We'll spend more time on this next week, so I'll finish up shortly. So we've got reactants goes to products.